Hello there, and welcome to Nocturnal Curiosity. Tonight we drift into the ancient and extraordinary world of the ocean, the deep memory of our planet written in water. Long before cities were built or maps were drawn, the seas were already alive, reshaping coastlines in silence. Waves carved cliffs and carried sand. Currents wandered across the globe like slow rivers without banks. Strange creatures glowed in darkness where sunlight had never reached. The ocean beneath the surface you imagine is ancient beyond measure, and yet it is still moving, still breathing, still changing. This is the story of the sea, a story of salt and pressure, of creation and collapse, of beauty that takes millions of years to form. Beneath every wave, within every grain of shore sand, there are whispers of ancient seas, glaciers, and stars long dissolved into water. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the ancient ocean carry your thoughts. Let us begin. If you could look at Earth from space with fresh eyes, you would not call it Earth at all. You would call it ocean. More than 70% of the planet's surface lies beneath seawater, a vast blue world that wraps the continents in its embrace. From above, the land masses appear as islands scattered across an endless sea. The ocean is not one body of water, but 5 connected regions that flow into each other without a true boundary between them. The Pacific alone is larger than all the land on Earth combined. It holds so much water that if you melted every ice sheet and glacier, every river and lake, every cloud and raindrop, it would still represent only a fraction of what already fills the sea. To understand our planet is first to understand that we live on a water world. The land we stand on is the exception. The ocean is the rule. Run a glass of seawater through the finest laboratory instruments, and you would find traces of nearly every element on the periodic table. Gold, uranium, lithium, and manganese all dissolve into the sea in amounts too small to see, but vast enough to matter. The dominant ingredient is sodium chloride, ordinary table salt, which gives seawater its familiar taste. But dissolved alongside it are magnesium, calcium, potassium, sulfate, and bicarbonate in a chemical cocktail that has remained remarkably stable for hundreds of millions of years. Rivers carry minerals eroded from rock and deposit them in the sea. Volcanoes on the seafloor add heat and chemistry. Organisms pull elements from the water to build shells and bones. And when they die, those materials sink and settle, cycling back through the deep. The ocean is not a passive container. It is the world's largest chemistry laboratory, running reactions that govern climate, life, and the very air we breathe. Near the surface, where sunlight warms the water and wind stirs the waves, the ocean can feel welcoming. But descend only a few hundred meters, and the temperature drops dramatically. By the time you reach the deep sea, the water hovers just above freezing, a few degrees above the point where ice forms. This cold is not merely a curiosity. It drives one of the ocean's most powerful mechanisms, a global circulation system sometimes called the Great Ocean Conveyor Belt. In polar regions, cold water becomes dense and sinks to the bottom, pushing deeper layers aside and setting the entire ocean in slow motion. That motion carries heat, oxygen, and nutrients across the globe, connecting equatorial warmth to polar chill in an endless loop that takes roughly 1,000 years to complete a full circuit. The cold depths are not dead zones. They are the beating heart of a circulation that keeps the surface world alive. Imagine descending into the ocean as if reading the chapters of a book. The first layer, the sunlit zone, extends just 200 meters down and holds nearly all of the ocean's photosynthetic life. Sunlight still reaches here, and the water teems with plankton, fish, and color. Below it lies the twilight zone, where light fades to a pale blue glow, and organisms with no equivalent on land drift in dimness. Deeper still, the midnight zone begins, utterly dark, cold, and under tremendous pressure. Life here glows with its own light, hunting and hiding in the blackness. The abyssal zone stretches across the ocean's true floor, flat plains of mud where pressure would crush an unprotected human instantly. And at the very bottom, in the Hadal zone found only in the deepest trenches, creatures have evolved for millions of years in conditions more extreme than the surface of some planets. Each layer is a separate world, connected only by the slow rain of particles falling from above. We have better maps of the surface of Mars than we do of the bottom of our own ocean. But despite centuries of sailing and decades of research, the vast majority of the seafloor remains unmapped at high resolution and unexplored by human eyes. The deep sea covers an area larger than all of Earth's land combined, yet only a tiny fraction has been directly observed. Every expedition that descends into uncharted waters returns with something unexpected. New species discovered on a single dive can number in the dozens. Entire ecosystems found in places thought barren. Strange geological formations that rewrite textbooks. The ocean is not only Earth's largest ecosystem, it is also its greatest unknown. To say we know the sea is to misunderstand how vast a mystery it remains. The creatures, landscapes, and processes hidden beneath the waves may hold answers to questions we have not yet thought to ask. When Earth first formed from colliding dust and rock, there was no ocean. The planet was a molten sphere, far too hot for liquid water to exist on its surface. But as it cooled over hundreds of millions of years, volcanoes exhaled enormous amounts of water vapor that had been locked inside the rock. That vapor rose into the cooling atmosphere and eventually fell as rain. For millennia, it rained without stopping, filling basins and valleys with the first primitive seas. But volcanic outgassing alone may not fully explain how so much water arrived. Ancient meteorites called carbonaceous chondrites and comets carry water ice that matches the chemical signature of Earth's oceans. Some scientists believe that a bombardment of icy objects from the outer solar system supplemented the volcanic water, delivering the final ingredient. The ocean is not simply old. It is assembled from the universe itself. When you take a breath of air, you are filling your lungs with oxygen, produced partly by forests and partly by the sea. Tiny microscopic organisms called phytoplankton drift near the ocean surface and perform photosynthesis just as trees do, absorbing carbon dioxide and releasing oxygen. Their combined output is staggering. Scientists estimate that phytoplankton generates somewhere between 40 and 60% of all the oxygen in Earth's atmosphere. They are invisible to the naked eye, and yet their collective presence shapes the air of the entire planet. Without them, land-based life as we know it could not exist. These miniature factories also form the foundation of nearly every marine food chain. Every fish, whale, and seabird ultimately depends on them for energy. A bloom of phytoplankton can be seen from space as a swirling turquoise cloud in the surface water. These small lives make enormous things possible. Water is extraordinarily good at absorbing and releasing heat slowly, a property that makes the ocean one of the most important climate regulators on Earth. The sea absorbs more than 90% of the excess heat produced by the greenhouse effect, storing it in its vast depths and releasing it gradually. Without this buffer, surface temperatures would swing far more wildly between seasons and between day and night. Ocean currents carry warmth from the tropics toward the poles, moderating climates that would otherwise be far harsher. The mild winters of Western Europe are largely a gift from the Gulf Stream, a river of warm Atlantic water that flows northward along the ocean surface. The same current that warms England and Norway began its journey near the equator, carrying tropical heat thousands of kilometers before releasing it into the northern atmosphere. The ocean does not merely respond to climate, it creates it. In the western Pacific Ocean, east of the Mariana Islands, the seafloor drops away into a trench so deep it defies imagination. The Challenger Deep, the lowest known point in the ocean, lies nearly 11 kilometers beneath the surface. If you placed Mount Everest inside it, the summit would still be more than 2 kilometers underwater. The pressure at that depth is roughly 1,000 times greater than at the surface, enough to compress steel and crush the air from any lung. Yet in the 1960s, a small submersible called the Trieste descended all the way to the bottom, and the crew found life there. A flatfish resting on the sediment, a shrimp swimming through the darkness. Life had found a way even at the extreme end of what the planet can offer. Today, specially designed vehicles continue to explore this trench, finding microorganisms in the sediment that reprocess organic material in ways that affect chemistry throughout the ocean. Descend below a few hundred meters of ocean water, and the last traces of sunlight disappear. The world becomes absolute black. Yet it is not dark in the way a windowless room is dark. The deep sea glows. An estimated 70 to 90% of deep-sea organisms produce their own light through a chemical reaction called bioluminescence. Anglerfish dangle glowing lures to attract prey. A squid flash patterns that communicate or confuse. Jellyfish pulse with ghostly blue rings. Small crustaceans leave trails of shimmering particles when disturbed. Even the seawater itself can glow when agitated, a phenomenon sailors have described for centuries. The chemistry behind this glow involves a molecule called luciferin that reacts with oxygen to emit light without producing heat. This cold fire has evolved independently dozens of times across vastly different animal groups, suggesting it solves a fundamental problem of survival in the dark. The deep ocean is a universe of living light. Much of the abyssal plain, the vast flat floor of the deep ocean, is covered in a layer of fine sediment called marine snow. This is not snow in the familiar sense. It is a continuous gentle rain of organic particles falling from above. Dead plankton, fecal pellets, fragments of larger organisms, and mineral dust all drift slowly downward through kilometers of water, taking days or weeks to reach the bottom. When they arrive, they accumulate into a soft, dark mud that builds up at the rate of just a few millimeters per 1,000 years. Objects that fall to this plane sink into it slowly, sometimes disappearing entirely over centuries. The sediment preserves a record of everything that has passed through the water column above it. Scientists drill into this archive to read past climates, ancient productivity levels, and the history of the ocean itself. Every layer of mud is a page in a book, that stretches back millions of years. Beneath the surface currents visible from satellites and ships, the ocean moves in hidden ways. Along the continental shelves and down submarine canyons, dense, sediment-laden water sometimes flows in powerful underwater rivers called turbidity currents. When triggered by earthquakes or the slow buildup of sediment, these currents can race across the seafloor at speeds exceeding 100 kilometers per hour, carrying enormous volumes of sand and debris far into the deep. They have snapped underwater communication cables, carved submarine canyons as large as any on land, and deposited sediment fans the size of small countries on the abyssal plain. The largest known turbidity current carved the Laurentian fan off the coast of Canada, spreading sediment across an area larger than France. These invisible rivers reshape the ocean floor in moments that take the visible landscape years to match. They are the hidden landslides of a planet mostly covered in water. Run your finger along the floor of the Atlantic Ocean, and you would trace a chain of mountains stretching from the Arctic to the Southern Ocean, and then across the Indian and Pacific Oceans. The mid-ocean ridge system is over 60,000 kilometers long, the most extensive mountain range on Earth, and almost entirely hidden beneath the sea. At its crest, tectonic plates pull apart and molten rock wells upward, building new ocean floor. The mountains themselves rise several kilometers above the surrounding plain. In places where the ridge breaches the surface, it forms islands like Iceland and the Azores. Volcanic activity along the ridge is continuous. New rock forms, cools, and spreads outward. The sea floor is a conveyor belt that carries crust away from the ridge until it eventually sinks beneath a continent at a subduction zone. Every few centimeters of ocean floor was once red-hot magma rising from the ridge below. Along the mid-ocean ridge, where plates pull apart and hot rock nears the surface, seawater seeps into cracks in the crust. It travels downward until it nears the heat of the mantle, where it superheats far beyond the normal boiling point, held in liquid form only by the immense pressure below. Then it rises rapidly back through the rock, picking up dissolved minerals along the way. When it vents into the cold ocean, it emerges as a black or white cloud of mineral-rich fluid called a hydrothermal vent. Around these vents, communities of life have evolved that depend entirely on chemistry rather than sunlight. Chemosynthetic bacteria form the base of a food chain that includes giant tube worms 2 meters long, eyeless shrimp, pale crabs, and translucent fish. Every organism here is powered by heat and minerals from the planet's interior. These ecosystems are among the most isolated on Earth, and they have changed how we think about the boundaries of life. Sound travels through water about 4 times faster than it does through air, and at certain depths, it barely loses intensity at all. In the middle of the ocean, there exists a layer called the SOFAR channel, short for sound fixing and ranging, where pressure and temperature combine to create an acoustic highway. Sound entering this channel can travel thousands of kilometers, wrapping around the globe like a whispered message in a cathedral. Whales exploit this property to communicate across ocean basins. The deep calls of blue and fin whales, recorded below the range of human hearing, can travel from one hemisphere to another. Scientists have used the SOFAR channel to monitor distant underwater earthquakes, and even to measure global ocean temperatures by tracking how quickly sound travels through warming water. The ocean is full of sound. Most of it is biological, the clicks and songs of creatures navigating, hunting, and communicating in a world where darkness makes hearing more important than sight. Before blue whales existed, the largest animals on Earth were dinosaurs. The blue whale surpasses even the most massive of them. Adults can grow to over 30 meters in length and weigh as much as 180 metric tons, roughly the equivalent of 30 elephants. A heart the size of a small car pumps blood through a body so vast that a human could crawl through its largest arteries. Yet, this giant feeds on krill, crustaceans no larger than a finger. It takes enormous mouthfuls of water, filters out the tiny animals, and swallows them by the millions. During feeding season, a single blue whale consumes up to 4 tons of krill each day. Despite their enormity, blue whales are elusive, found in every ocean, but never in large groups. Their low-frequency calls can be detected thousands of kilometers away. They were nearly hunted to extinction in the 20th century. Today, their numbers are recovering, slowly and quietly, somewhere in the deep blue. Among the ocean's most haunting sounds are the songs of humpback whales. These complex vocalizations can last for 20 minutes to several hours, with patterns that repeat and evolve over the course of a breeding season. All the males in a given region sing the same song, but the song changes gradually from year to year, with new phrases spreading from whale to whale like a slowly evolving tradition. No one is entirely sure what the songs communicate. They appear connected to reproduction, but the precise message remains uncertain. What scientists do know is that these calls, which travel through the SOFAR channel, can be heard by other whales thousands of kilometers away. A whale singing off Hawaii may be answering a call that originated near Alaska. The ocean is an acoustic world, and whales are among its most eloquent speakers, filling the dark water with compositions that have no parallel on land. And no animal on Earth changes its appearance more dramatically or more quickly than the octopus. In under a second, an octopus can shift from pale ivory to deep brown, from smooth skin to a forest of textured bumps, from a rounded blob to a shape that mimics rock, algae, or even other animals. This ability is controlled by millions of color-changing cells called chromatophores, which expand and contract under direct neural control. The octopus does not see color in the conventional sense. Its eyes lack the color receptors humans have, yet it produces color displays of astonishing accuracy. Scientists believe it may sense color through photoreceptors in the skin itself. The intelligence behind this camouflage is equally remarkable. Octopuses solve puzzles, use tools, learn from watching others, and play. A behavior once thought unique to mammals and birds. In the ocean's shallow reefs, these 8-armed creatures are among the most cognitively complex animals alive. A coral reef that looks like solid rock is actually alive. Each branching arm and rounded dome is made of countless tiny polyps, soft-bodied animals smaller than a fingernail. Each polyp builds a limestone cup around itself for protection, and when it dies, the cup remains. New polyps grow on top of old ones, layer by layer, colony by colony. The reef rises toward the sunlight over centuries and millennia. The Great Barrier Reef, off the coast of Australia, stretches more than 2,000 kilometers, making it the largest biological structure on Earth, large enough to be seen from space. Despite covering less than 1% of the ocean floor, coral reefs support roughly a quarter of all known marine species. They are the tropical rainforests of the sea. Each coral polyp maintains a relationship with microscopic algae called zooxanthellae that live in its tissues, sharing the products of photosynthesis in a partnership that powers the entire reef ecosystem. Every year, human activity releases billions of tons of carbon dioxide into the atmosphere. Without the ocean, that gas would accumulate far faster than it does. The sea absorbs roughly 30% of all anthropogenic carbon dioxide, sequestering it in its depths through a combination of physical and biological processes. At the surface, carbon dioxide dissolves directly into the water. In the sunlit zone, phytoplankton absorb it during photosynthesis and incorporate it into organic matter. When those organisms die, some of that carbon sinks to the deep ocean in what scientists call the biological pump, removing it from the atmosphere for centuries or millennia. This service is enormous and largely invisible. The ocean is the planet's most important carbon sink, but it comes at a cost. As more carbon dioxide dissolves into seawater, the ocean becomes more acidic. This process, called ocean acidification, threatens the calcium carbonate structures of corals, mollusks, and many plankton that underpin marine food webs. Since the mid-20th century, the global ocean has risen by roughly 20 centimeters, and the rate is accelerating. Two processes are responsible. The first is thermal expansion. As seawater warms, it expands slightly in volume. The second is the melting of land-based ice. Glaciers and ice sheets on Greenland and Antarctica are losing mass at increasing rates, and that meltwater flows into the ocean, raising its level. For coastal communities and low-lying islands, even small rises in sea level can be catastrophic. Storm surges that once flooded once a century may flood annually. Salt water intrudes into freshwater aquifers. Beaches erode and islands shrink. The ocean does not care about borders or economies. It rises steadily, carrying the thermal signature of every ton of greenhouse gas released into the atmosphere. The sea is the planet's memory of warming, and it records that memory in the slow, patient rise of its surface. If you could trace the journey of a single drop of water through the ocean, you would follow it on a voyage lasting roughly 1,000 years. Beginning near the surface in the tropics, it would be carried north by warm surface currents. In the far North Atlantic, it would cool, become denser, and sink to the bottom. From there, it would flow south through the deep Atlantic, around the tip of Africa, across the Indian Ocean, and into the Pacific. Eventually, it would rise in upwelling regions along the coasts and return to the surface, warmed by the tropics, to begin the cycle again. This grand circuit is called thermohaline circulation, driven by differences in temperature and salinity. It distributes heat from equator to poles, carries oxygen into the deep, and brings nutrients to the surface, where life needs them most. If this circulation were to slow significantly, the climate consequences would reach every corner of the globe. Every few years, a warming of the central and eastern tropical Pacific Ocean shifts wind patterns, ocean currents, and rainfall across the entire planet. This phenomenon, called El Niño, can bring devastating floods to Peru and California, while plunging Indonesia and Australia into drought. It weakens the monsoon over India, warms winters in the northern United States, and strengthens hurricanes in the Pacific while suppressing them in the Atlantic. The scale of disruption from a single shift in ocean temperature is staggering. Its counterpart, La Niña, reverses these effects, cooling the same region and producing roughly opposite results. Together, these two phases form the El Niño Southern Oscillation, the most powerful year-to-year climate signal on Earth. Every drought, flood, and storm season is nudged by the state of the Pacific Ocean, The sea does not merely respond to the atmosphere. It dictates to it in a slow, irregular rhythm that has shaped human history for thousands of years. When fresh water freezes, ice forms at the surface and insulates the water below, allowing fish to survive the winter beneath a frozen lid. Seawater behaves differently because dissolved salt lowers its freezing point. As surface water cools, it becomes denser and sinks, bringing slightly warmer water up from below in a constant mixing. When the ocean finally does freeze, the resulting ice is different in structure and behavior. Sea ice is full of tiny channels filled with extremely salty brine that drains downward as the ice forms, creating cold, dense water that sinks to the bottom and drives deep circulation. In the channels that remain, specialized algae and bacteria survive in one of the harshest habitats on Earth, and they form the base of an ice-dependent food chain that includes krill, fish, seals, and polar bears. The freezing ocean is not a dead place. It is a strange and specialized ecosystem, shaped entirely by the physics of salt and cold. A large iceberg carves from a glacier in Greenland or Antarctica as an island of freshwater ice the size of a small city. It sets off on a journey that may last for decades, driven by currents and winds across thousands of kilometers of open ocean. As it travels, it melts from below and above, releasing fresh water that lowers the salinity of surrounding seas and feeds blooms of phytoplankton with iron-rich glacial meltwater. The most massive icebergs, called tabular bergs, are break from the ice shelves of Antarctica and can exceed the size of some European countries. One iceberg tracked by satellites drifted from Antarctica across the Atlantic and into the Southern Ocean before finally dissolving. The melting of these frozen giants is accelerating as ocean temperatures rise. Each disappearing iceberg represents fresh water that was locked in glacial ice for thousands of years, now returning to the sea in a matter of years. In the middle of the North Atlantic Ocean lies a sea defined not by land, but by water. The Sargasso Sea is bounded on all sides by ocean currents. The Gulf Stream to the west, the North Atlantic Current to the north, the Canary Current to the east, and the North Atlantic Equatorial Current to the south. These currents trap a swirling body of warm, clear, nutrient-poor water in the middle. The sea is named for the sargassum, a brown seaweed that floats on its surface in enormous golden mats, forming a unique ecosystem found nowhere else on Earth. Juvenile sea turtles hide in the mats. Seahorses cling to fronds. Tiny fish, crabs, and invertebrates, evolved specifically for life in floating seaweed, make this one of the strangest habitats on Earth. The European eel migrates thousands of kilometers to spawn in the Sargasso Sea, and its larvae drift on currents back to the rivers of Europe, a journey lasting years. From the coast of Peru to the shores of the Philippines, the Pacific Ocean stretches more than 19,000 kilometers, nearly halfway around the Earth at the equator. It is wider than the distance from Earth to the Moon. Its area exceeds that of all the world's land masses combined. Within it lie more than 25,000 islands, forming the most island-rich ocean on the planet. The deepest, the highest, the most volcanically active points of the ocean floor all exist within its bounds. It holds more than half of all the water in the world's oceans. The Pacific was once considered so vast and featureless that early European navigators doubted they could cross it alive. The Pacific Islanders of Polynesia, Micronesia, and Melanesia navigated it thousands of years ago without instruments, guided by the stars, the waves, the wind, and the behavior of birds. Their knowledge of the ocean was as detailed as any map. When you watch a wave roll toward the shore, it appears that water is traveling toward you. It is not. What travels is energy. The water itself moves in circular orbits, rising as a wave passes and falling back down without actually moving forward. This is why a floating piece of seaweed bobs up and down in place as waves pass beneath it rather than being carried to shore. Waves are born far out at sea when wind transfers energy to the water surface. A sustained wind over a long stretch of open ocean, called the fetch, builds waves progressively larger over time. The largest waves ever reliably measured reached over 30 meters in height during severe storms in the Southern Ocean. Even these giants are patterns of energy moving through water, not rivers of water moving across the sea. When waves finally reach shallow water near a coast, the circular motion is compressed, the wave slows and steepens, and the energy that traveled thousands of kilometers is finally released in a crash of foam. When a massive earthquake ruptures a fault beneath the ocean floor, it can displace an enormous volume of water vertically. That displacement radiates outward as a tsunami, not a single wave, but a series of long wavelength pulses that travel across entire ocean basins. In open water, a tsunami may be barely noticeable, just a gentle rise of a meter or less, moving at the speed of a commercial airliner. A ship at sea would pass over one without the crew ever noticing. But the true danger lies at the coast. As the wave enters shallow water, it slows and its energy compresses upward. What was a ripple in deep water becomes a wall of water that can surge inland for kilometers, carrying everything before it. The 2004 Indian Ocean tsunami killed over 200,000 people and was felt as far away as Antarctica. The energy released in that earthquake was equivalent to thousands of nuclear weapons detonating simultaneously beneath the sea. Most people think of ocean currents as simple streams moving at a steady pace near the surface. In reality, the ocean interior is filled with complex swirling eddies, underwater weather systems that can persist for years. These rotating masses of water, some extending hundreds of kilometers across, trap and transport heat, salt, and nutrients as they travel. They form when major currents like the Gulf Stream shed spinning loops of water, the way a river sheds meanders. Within an eddy, the water rotates slowly, isolating its internal chemistry from the surrounding sea. Some eddies carry warm water into cold regions. Others draw cold water up from the depths, creating temporary patches of biological productivity. Satellites can detect their surface signature as slight variations in sea height. Beneath the surface, they are invisible and unmapped. The interior ocean is as dynamic and weather-driven as the atmosphere above it, just in slow motion. The underwater visual world is nothing like what we see above the surface. Certain fish and cephalopods perceive polarized light, a property of the way light waves oscillate that is invisible to human eyes. In water, polarized light patterns shift with depth, angle, and the position of the sun. And some animals use these patterns for navigation, prey detection, and communication. Mantis shrimp take this to an extreme. They have 16 types of photoreceptors, compared to 3 in the human eye, and can detect 12 different wavelengths of color, in addition to ultraviolet and polarized light. And their visual world contains color channels that have no names in any human language, because no human has ever seen them. In the ocean, sight evolved under completely different pressures than on land. The water absorbs red light quickly, leaving a blue world at depth. The visual systems of sea creatures are tuned to this environment in ways that make them genuinely alien to our experience. Long before the dinosaurs, before trees had fully evolved, before the first vertebrate had crawled onto land, sharks were already swimming in Earth's oceans. The earliest known sharks appear in the fossil record around 450 million years ago, predating even the mass extinction that wiped out more than 90% of marine species. While those extinctions remade the ocean around them, sharks survived and continued. The modern forms we recognize evolved over a much shorter timescale. But the basic blueprint of a cartilaginous predator with an excellent sensory system and efficient body form has barely changed in hundreds of millions of years. Sharks detect electric fields generated by living muscles, can smell a single drop of blood diluted across an enormous volume of water, and feel pressure changes through their lateral line system. They are perfectly engineered by 400 million years of testing, refined through every extinction the planet could throw at them. In the middle of the Pacific Ocean, rising from the ocean floor, is the volcano Mauna Kea. Its summit sits 4 kilometers above sea level, high enough that it receives snow in winter. But measured from its base on the seafloor, Mauna Kea rises more than 10 kilometers, and making it the tallest mountain on Earth by that measure, surpassing even Mount Everest. The ocean hides dozens of such giants, seamounts, underwater volcanoes that did not quite reach the surface, rise thousands of meters from the abyssal plain and form isolated habitats that attract concentrations of marine life. Their slopes create upwelling zones where nutrient-rich deep water rises to the surface, fueling blooms of productivity. Many seamounts were discovered only in the past few decades, mapped by sonar from research vessels crossing waters thought to be featureless. Each one is a mountain in the dark, and like all mountains, it changes the weather around it, the currents that flow past it, and the life that clings to it. Jellyfish have drifted through Earth's oceans for at least 500 million years, are making them among the oldest multicellular animal groups known. They predate the dinosaurs by nearly 300 million years and have outlasted every mass extinction the planet has experienced. They achieve this longevity without any of the machinery we associate with complex life. No brain to process information, no heart to pump fluid, no blood to carry oxygen. Instead, they have a simple nervous system that coordinates their pulsing bell, a diffuse network of cells that senses light, gravity, and chemistry without anything resembling thought. Their bodies are roughly 96% water. Some species grow no larger than a thumbnail. Others, like the lion's mane jellyfish, trail tentacles over 30 meters long. The Turritopsis dohrnii, a small species from the Mediterranean, can revert to its juvenile form after reaching sexual maturity, effectively resetting its life cycle and potentially living indefinitely under the right conditions. Ocean crust does not last forever. At subduction zones around the Pacific Ocean and elsewhere, dense ocean crust dives beneath lighter continental crust and plunges back into the mantle, where it melts and joins the molten rock below. This process is relentless and continuous. The Pacific Ocean is shrinking by several centimeters each year as its floor disappears beneath Asia, the Americas, and the chains of island arcs that mark the subduction boundary. The same process builds the volcanoes of the Pacific Ring of Fire and generates the earthquakes that regularly shake Japan, Chile, and Alaska. No ocean floor is older than about 200 million years. A brief moment in the 4.5 billion year history of the planet. The Mediterranean seafloor is actively disappearing beneath southern Europe, a process that will eventually close the Mediterranean entirely and build a mountain range where the sea now lies. Walk across a desert in the American Southwest and look at the layered cliffs rising around you. Many of those layers are limestone, and limestone forms from the accumulated shells of marine organisms in warm, shallow seas. The stone beneath your feet was ocean floor. Fossils of coral, clams, and sea creatures appear in desert rock, in mountain peaks, in the chalk cliffs of Dover, and the Cretaceous beds of Texas. Throughout Earth's long history, seas have advanced and retreated over the continents dozens of times. The interior of North America was covered by a shallow sea called the Western Interior Seaway, as recently as 65 million years ago. The land we consider permanent has been sea floor more times than it has been dry ground. To walk across ancient limestone is to walk across a vanished ocean, its creatures compressed into stone, its chemistry locked in rock, its memory preserved in every fossil and every grain of sediment. Far above the ocean floor, invisible to any ship or swimmer, a constant gentle rain of organic particles drifts slowly downward through the water column. Scientists call it marine snow, and it is one of the ocean's most important processes. It consists of dead plankton cells, fecal pellets, shed mucus, tiny mineral grains, and clumps of organic material that aggregate on their way down. A single flake of marine snow might take weeks to drift from the sunlit zone to the seafloor. As it falls, bacteria and small animals consume portions of it, extracting nutrients and energy. What arrives at the bottom is a transformed version of what began at the surface. This slow rain is the primary mechanism by which the ocean exports carbon from the surface to the deep. It is the biological pump that removes carbon dioxide from the atmosphere and buries it in sediment. Without marine snow, the ocean's role as a carbon sink would be far smaller and the atmosphere far warmer. In the freezing waters of the Arctic Ocean, a whale swims with a single spiraling tusk projecting forward from its head. The narwhal's tusk, which can grow to over 3 meters long, is actually an overgrown tooth, specifically a canine that pierces the upper lip and continues growing in a counterclockwise spiral. For centuries, Europeans believed the tusks were the horns of mythical unicorns and traded them at extraordinary prices. Science eventually revealed the truth, which is no less remarkable than the legend. The tusk is filled with millions of tiny nerve endings that connect to the outside world, making it an extraordinary sensory organ. Narwhals have been observed using their tusks to detect pressure, temperature, salinity, and particle gradients in the water, essentially tasting the ocean around them. They also use them in social interactions and sometimes in competition. The tusk is both tool and organ, a biological instrument tuned to the Arctic waters over millions of years of evolution. At the bottom of the Mariana Trench, the pressure is over 1,000 times greater than at sea level. A human body taken to that depth without protection would be crushed instantly. Yet the creatures that live there experience that pressure as normal. Hadal fish, the term for those found in the deepest ocean trenches, have evolved biochemistry that functions precisely under those conditions. Their proteins would fall apart under lower pressures. Their cell membranes are composed of different lipids than shallower fish, keeping them fluid rather than solid under extreme cold and pressure. The snailfish, a small, pale creature that looks unremarkable, has been found living deeper than any other vertebrate, more than 8 kilometers beneath the surface. It feeds on shrimp and small crustaceans that fall into the trench. These fish are not surviving difficult conditions. They are perfectly adapted to conditions that are extreme only from a surface perspective. In the Cold War, when submarines needed to communicate across ocean basins without being detected, they exploited a physical property of the sea that had been discovered decades earlier. The SOFAR channel, a depth layer where sound travels exceptionally efficiently, allowed submarines to send coded acoustic signals thousands of kilometers with minimal loss of signal strength. This same channel carries the low-frequency calls of whales, allows distant hydrophones to detect underwater earthquakes, and has been used by scientists to monitor changes in ocean temperature by measuring how quickly sound travels through warming water. The channel exists because sound speed depends on temperature and pressure. Below the warm surface, temperature decreases and slows sound. But at greater depths, rising pressure speeds it again. At the depth where these two effects balance, the SOFAR channel forms a natural acoustic waveguide. It is an invisible structure in the ocean, detectable only with instruments, used by creatures that evolved millions of years before humans ever thought to listen. Dissolved in the vast volume of the world's oceans is an extraordinary quantity of gold. Scientists estimate that approximately 20 million tons of gold exist in a dilute concentration throughout the sea, along with nearly every other element in the periodic table. The concentration is so low, just a few parts per trillion, that no economical method exists to extract it. The sheer volume of water more than compensates for the dilution. This gold was not deposited there in any single event. It has accumulated over billions of years as rivers eroded it from rock, as hydrothermal vents added mineral-rich water, and as meteorite impacts contributed metals from space. The same process that keeps gold too diffuse to extract also cycles nutrients essential to life. The ocean is not merely a container of dissolved minerals. It is a dynamic system in which everything is connected. The gold that cannot be mined is part of a chemistry that sustains the plankton that produce the oxygen in the air above it. In the shallow coastal waters and seagrass meadows of the world's temperate and tropical seas lives one of the ocean's most improbable creatures. The seahorse, despite its name, is a true fish. It breathes through gills, has a swim bladder, and is classified among the ray-finned fishes. But almost everything else about it defies expectation. It swims upright, propelled only by a small dorsal fin, beating dozens of times per second. It uses its prehensile tail to grip seagrass against currents. It has no stomach, meaning it must eat almost constantly to survive. But most remarkable is its reproductive strategy. The female seahorse deposits her eggs into a brood pouch on the male's belly, where he fertilizes them, nourishes them through a network of blood vessels, and carries them until birth. Some species give birth to over 1,000 miniature seahorses in a single event. The male carries every pregnancy. In the animal kingdom, this reversal of reproductive roles is extraordinarily rare. Beneath the ocean surface, the seafloor is not a uniform plain, but a landscape as varied as any continent. In several locations around the world, brine pools sit on the ocean bottom like underwater lakes, filled with water so dense in salt and methane that it does not mix with the surrounding seawater. They have a distinct surface and shore. Strange organisms evolved specifically for their extreme chemistry live in the brine or at its edges. Where cold, dense water flows over a submarine ridge, it cascades down the other side in a waterfall. The Denmark Strait Cataract, a waterfall of cold Arctic water plunging into the Atlantic, drops over 3.5 kilometers, making it the tallest waterfall on Earth by height. It carries a volume of water roughly 5 times greater than the flow of the Amazon River. These underwater landscapes, waterfalls, lakes, and rivers are hidden expressions of the same physics that shapes the visible world above, just operating in a medium that makes them nearly impossible to see. In the shallow coastal waters of nearly every continent on Earth, beds of seagrass spread across sandy and muddy seafloors, their slender green blades swaying with the current. Seagrasses are not seaweeds. They are flowering plants, the only true plants that have returned to the ocean from land. Their roots anchor sediment, their blades slow water flow, and their dense meadows provide nursery habitat for fish, sea turtles, and manatees. But their most important ecological role may be one invisible to the naked eye. Seagrass meadows sequester carbon at rates up to 35 times greater than tropical rainforests per unit area. They achieve this by burying organic matter in their dense root systems and in the stable, low-oxygen sediment beneath them, where decomposition is slow. Scientists call this blue carbon, a distinction from the carbon sequestered in forests. Yet seagrass meadows are disappearing faster than rainforests, lost to pollution, boat anchors, and coastal development, taking their carbon stores with them. The ocean is not a uniform bowl of water. It is stratified into invisible horizontal layers, separated by abrupt boundaries called thermoclines and haloclines, where temperature and salinity change sharply within just a few meters. In tropical oceans, a warm surface layer sits atop a cold, deep layer, like oil over water, resisting mixing. This stratification means that nutrients trapped in the cold depths cannot rise easily to the sunlit surface where life could use them. In contrast, polar oceans mix more freely, bringing nutrients to the surface and supporting extraordinary biological productivity. Submarines exploit thermoclines to hide from sonar, since sound refracts off the density boundary in ways that create acoustic shadows. Fish navigate these invisible layers, hunting where cold upwelling brings prey to the surface. The ocean's layered structure is fundamental to how it distributes heat, oxygen, and nutrients. It is as important to the sea as weather fronts are to the atmosphere, shaping everything that lives within it. Along the tropical and subtropical coastlines of more than 100 countries, mangrove trees grow in the brackish zone between land and sea, and their tangled root systems rising from muddy tidal flats like natural cathedrals. These are some of the most productive ecosystems on Earth, sheltering juvenile fish and shrimp, sequestering carbon in their dense peat soils, and filtering pollutants from coastal water. But mangroves also provide a service that engineers are still struggling to replicate. Their dense root networks dissipate wave energy, reducing storm surge height by as much as half in some studies. During the 2004 Indian Ocean tsunami, villages protected by intact mangrove forests suffered less flooding and damage than those where the forests had been cleared. A living wall of trees can outperform a concrete seawall while simultaneously providing habitat and food. Yet mangroves are being lost to coastal development, shrimp farming, and sea level rise at rates that leave coastlines increasingly vulnerable to the storms that are growing stronger as the ocean warms. Each year, a small seabird weighing barely 100 grams makes a journey that no other animal on Earth attempts. The Arctic tern breeds in the Arctic during northern summer, then flies all the way to Antarctica to experience southern summer and returns. The round trip covers roughly 70,000 kilometers, and some individuals have been tracked flying even farther by following favorable wind patterns. Over a lifetime that can exceed 30 years, a single Arctic tern may travel a distance equivalent to 3 trips to the moon and back. These birds experience more daylight than any other animal on Earth, living almost perpetually in polar summer. They navigate by the sun, the stars, and Earth's magnetic field. Banded birds have been recovered after decades of making this same journey without fail. The migration is fueled by the rich marine life of polar seas. The tern is a bird of the ocean as much as the sky, plunging into the waves for fish that sustain the extraordinary energy demands of its endless flight. Deep within the sediment of the ocean floor lies an archive of planetary history, so detailed and so complete that it has rewritten our understanding of climate change. Every layer of sediment preserves chemical and biological information about the conditions of its time. The oxygen isotopes in tiny shells of foraminifera reveal ancient ocean temperatures. The presence or absence of certain species marks shifts in ocean chemistry and productivity. Iron particles from distant volcanic eruptions are preserved in exact layers. Dust from ice ages leaves visible bands in tropical sediment. Scientists drill cores of this sediment from research ships, extracting cylinders of material that represent millions of years of continuous deposition. By analyzing these cores, they have reconstructed the history of ice ages, warm periods, ocean acidification events, and mass extinctions. The ocean remembers everything that has happened to this planet. Its sediment is the most comprehensive record of Earth's past that exists, written not in words, but in chemistry and bone. For most of Earth's history, oxygen was not a feature of the atmosphere or the ocean at all. Life arose and diversified in an anaerobic world, powered by other chemical reactions. Even today, certain regions of the ocean, they're called oxygen minimum zones, contain so little dissolved oxygen that most animals cannot survive there. But some organisms thrive precisely in these low oxygen environments. Bacteria called anaerobes use sulfate or nitrate for respiration instead of oxygen, producing hydrogen sulfide as a byproduct. In the sediments of the Black Sea and in basins off the coasts of Chile and Namibia, entire communities of microorganisms exist without any oxygen whatsoever. In 2010, scientists discovered multicellular animals called loricifera living in anoxic sediment in the Mediterranean, the first complex animals known to complete their life cycle without oxygen. These discoveries push the boundaries of what we define as habitable. Life in the ocean does not merely tolerate the unexpected, it exploits it. The ocean of today is fundamentally different from the ocean of 3 billion years ago. In the early Archean eon, seawater contained almost no oxygen and was rich in iron, sulfide, and other reduced compounds that would be toxic to most modern life. The rise of photosynthetic bacteria slowly transformed that ancient sea, releasing oxygen that first reacted with the dissolved iron, turning it to rust and depositing the banded iron formations we mine today. Only after all the iron was oxidized did oxygen begin accumulating in the atmosphere. Later intervals brought their own changes. Warmer periods saw shallower, more evaporated seas with higher salinity. Colder periods produced different chemistry as glaciers locked water away. Mass extinction events left chemical signatures in the sediment. The ocean has never been static. It has co-evolved with the atmosphere and with life, each shaping the other in a feedback that has lasted 4 billion years. The sea you imagine is one snapshot in an ongoing transformation. Every time a research vessel deploys nets or cameras in unexplored parts of the deep ocean, it returns with something unknown to science. New species are described from the ocean at a rate that would be remarkable even if the ocean were well explored. Given how little of it has been sampled directly, the true number of undescribed species is likely staggering. Estimates suggest that the ocean may contain anywhere from 500,000 to 1 million or more species still waiting to be identified. Many of these will be microorganisms, bacteria, and archaea, with biochemistries unlike anything studied in laboratories. But larger animals are still being discovered too. The giant squid, once thought a myth, was first photographed alive in its natural habitat only in 2004. New species of beaked whale have been described within the past few decades. The ocean is not merely hiding secrets. It is full of entire taxonomies we have not yet encountered. Our knowledge of life on this planet is incomplete in direct proportion to how little of the ocean we have explored. For roughly the first 4 billion years of life on Earth, the ocean was its only home. Single-celled organisms appeared in the sea. Multicellular life evolved there. The first animals with symmetry and organs, the first creatures with eyes, the first predators and prey, all originated in the ocean. The Cambrian explosion, the rapid diversification of complex animal body plans that began roughly 540 million years ago, happened entirely underwater. Fish evolved in the ocean before the first vertebrate crawled onto land. Insects and reptiles, and eventually mammals, all trace their ancestry back to ocean ancestors. Even the plants that colonized land did so, from green algae that first mastered photosynthesis in shallow seas. The ocean is not merely an ecosystem. It is the evolutionary nursery from which all complex life on Earth emerged, shaped by selection pressures that remain unchanged in many parts of the deep sea. Every creature on land carries within its biology the memory of the sea. Before hydrophones began recording the ocean's interior in the 20th century, people imagined the deep sea as a world of absolute silence. The truth is precisely the opposite. The ocean is filled with sound. Whales sing and click and groan. Shrimp colonies snap their claws in coordinated bursts that generate sounds louder than a jet engine. Fish produce grunts, croaks, and whistles for communication, courtship, and territory defense. The sea floor itself creaks and rumbles with geological activity. Distant earthquakes send low-frequency tremors through the water. Rain creates a hiss at the surface. Even ice cracking in polar seas produces sounds that travel thousands of kilometers. Human noise from shipping, sonar, and industry has added a new layer that many marine animals must now compete with. The ocean's soundscape is a complex symphony that has been playing for hundreds of millions of years, layered and intricate, filled with communication that we are only beginning to decode. At the edge of the sea, where waves wash and recede twice each day, lie some of the most productive and biologically diverse habitats on Earth. Tidal pools are small pockets of seawater trapped in rock depressions between tides. In a pool no larger than a bathtub, dozens of species may coexist. Sea stars hunt mussels. Hermit crabs scavenge what the tide leaves behind. Anemones filter plankton with waving tentacles. Periwinkles rasp algae from rock surfaces. Gobies hide in crevices, while blennies leap between pools. Every creature in a tidal pool must survive conditions that swing between extremes. Twice a day, fresh seawater replenishes the pool. Between tides, the water may warm in the sun, cool in fog, grow more saline as it evaporates, or freshen with rain. Then the organisms that live there are among the most environmentally resilient on Earth, adapted to unpredictability in ways that make them ideal subjects for understanding how life responds to change. Maps divide the ocean into the Pacific, Atlantic, Indian, Southern, and Arctic. But these boundaries are human inventions. Water does not respect lines drawn on paper. The ocean is one continuous body, connected at every boundary, exchanging water, heat, salt, and life across every imaginary division. A molecule of water evaporated from the tropical Indian Ocean may fall as rain in the Amazon, flow to the Atlantic, drift northward in a surface current, sink in the North Atlantic deep water, travel along the ocean floor to the Pacific, and rise in an upwelling off the coast of Peru. This journey takes hundreds of years. During it, that water molecule has participated in every part of the ocean's chemistry, helped sustain countless organisms, influenced the climate of 3 continents, and recorded the conditions of every ocean it passed through. The 5 named oceans are one ocean wearing different names. It has no beginning and no end. It simply moves, always. The ocean that exists today is not the ocean of 100 years ago, and it will not be the ocean of 100 years from now. Sea surface temperatures have risen by more than 1 degree Celsius since the industrial era began, fundamentally altering the distribution of marine species, shifting the range of fisheries, bleaching coral reefs that took thousands of years to build. The ocean is more acidic than it has been in at least 800,000 years, and threatening the calcification of everything from oysters to the plankton that underpin food webs. Oxygen minimum zones are expanding as warmer water holds less dissolved gas. These are not predictions, they are measurements. The ocean is changing at a pace that has no parallel in the recent geological record, driven by the release of greenhouse gases that the sea itself is struggling to absorb. The future of the ocean is uncertain, but the ocean itself is patient. It has survived every catastrophe Earth has ever experienced. Whether the life within it can adapt quickly enough is the question that defines this era. Geology and oceanography are not separate sciences. They are chapters of the same story. The plates that drift beneath the continents also shape the ocean basins. The volcanoes that build mountains also build islands and hydrothermal vents. The ice ages that carved valleys also changed sea level by hundreds of meters. The fossils in desert limestone were once ocean floor. The gold in a wedding ring may have arrived on Earth inside a meteorite that splashed into a primordial sea. Every drop of water, every breath of oxygen, every chemical cycle that sustains life on Earth passes through the ocean at some point. The sea is not a boundary at the edge of the world. It is the world's largest and most important organ, connected to everything, driving everything, remembering everything. To study it is to study the planet's past, present, and future simultaneously. The ocean does not simply contain the story of Earth. It is the story of Earth, written in salt and pressure and time. The ocean contains multitudes that no single mind can fully hold. In the same body of water where blue whales travel in near silence, bacterial cells divide by the millions in every drop. A single liter of seawater can contain more than 1 million bacteria. hundreds of thousands of archaea and tens of thousands of viruses. These invisible communities cycle nutrients, produce oxygen, and decompose organic matter on a scale that dwarfs all visible life. Yet in that same water column, krill swarm in clouds visible from space. Herring school in formations that shift and shimmer like living metal. And schools of tuna sprint at speeds exceeding 70 kilometers per hour. The ocean holds organisms ranging from viruses measured in nanometers to blue whales measuring 30 meters, coexisting in layers determined by depth, temperature, and light. This range of scale, from the unimaginably small to the largest creature that has ever lived, exists within a single connected system, driven by the same fundamental chemistry. Along the continental shelves of every ocean, the seafloor drops away abruptly into canyons carved by turbidity currents and ancient rivers. Some of these submarine canyons are among the largest topographic features on Earth. The Monterey Canyon off the coast of California descends more than 3 kilometers and stretches over 150 kilometers in length, comparable in scale to the Grand Canyon. The Congo Canyon, carved by the outflow of the Congo River, cuts across the continental shelf and slope for nearly 800 kilometers, one of the longest submarine canyons known. These features are not merely geological curiosities. They funnel sediment and organic matter from the shallow shelf into the deep ocean, creating pathways for nutrients that sustain life along their walls and at their mouths. The walls of submarine canyons harbor cold water corals, sponges, and dense communities of invertebrates that exist in the dark water, far from any sunlight, fed by currents that sweep organic material down from the shelf above. When scientists measure the amount of heat that the Earth has absorbed due to increased greenhouse gases, more than 90% of that heat has gone into the ocean rather than the atmosphere. The sea's enormous heat capacity means that it acts as a vast buffer, absorbing warming that would otherwise have raised air temperatures far more dramatically than it has. This buffer comes with a cost. The heat stored in the ocean does not simply disappear. It will eventually return to the atmosphere as ocean temperatures equilibrate with the new energy balance. Even if greenhouse gas emissions stopped entirely today, the ocean would continue releasing stored heat for decades, driving further warming of the surface world. This delayed effect means that some amount of additional warming is already locked in, regardless of what actions are taken now. The ocean's patience, which has protected us from the worst consequences of warming so far, is also the reason that the consequences will outlast the cause by generations. In the polar oceans, where water temperatures can drop below the normal freezing point of blood and tissue fluid, fish face a unique biological challenge. Their blood and body fluids should freeze, yet they swim freely in water, cold enough to crystallize ordinary biological solutions. The solution that evolution found is remarkable. Antarctic icefish and certain Arctic fish produce antifreeze proteins, molecules that bind to ice crystals as they begin to form and prevent them from growing larger. The proteins work not by lowering the freezing point of the blood significantly, but by stopping ice propagation at the molecular level, inhibiting the growth of any crystal that forms. These proteins have been studied intensively for their potential applications in food preservation, organ storage for transplantation, and even crop frost protection. The chemistry that allows a fish to swim in sub-zero water was discovered through natural selection over millions of years of exposure to polar cold. Through a biological solution to a physical problem that human engineers are still trying to replicate. In the deepest layers of the ocean, far from the sunlight and wind that drive the surface world, there flows water that last contacted the atmosphere during the height of the last ice age. This ancient water sank from the polar surface when climate conditions were different, temperatures were lower, and the chemical signature of the air above reflected a world before industrialization. As it traveled through the deep ocean basins over centuries, it absorbed oxygen that will not be replenished until the water eventually rises back to the surface. Scientists can measure the age of deep water using radioactive carbon isotopes, tracing its journey from the surface downward. Some water in the deep Pacific is more than 2,000 years old. It carries within its chemistry a record of the surface conditions when it formed. This ancient water is not a relic. It is still active, transporting oxygen and nutrients into the deep sea, part of a circulation that has continued without interruption since before any recorded human history. In the great southern ocean that encircles Antarctica, there are no continents to block the winds or interrupt the waves. Storm systems generate swells that grow in the open water and travel northward through all three major ocean basins. A swell born in a winter storm near Antarctica can travel more than 15,000 kilometers before it reaches the beaches of California, Alaska, or Japan, arriving weeks later as a gentle rolling wave that gives no hint of the storm that created it. The energy in a swell travels in the direction of the wave's propagation, while the water itself moves in circles. As long as the swell moves through deep enough water, it barely diminishes at all. Surfers in California study wave forecasts that track Southern Ocean storms, precisely because the waves that arrive days later preserve their form and their energy across impossible distances. The ocean is a medium through which energy moves with extraordinary efficiency, carrying the memory of distant storms to shores that never felt the wind that made them. Where rivers meet the sea, something extraordinary happens. The mixing of fresh water and salt water creates estuaries, zones of transition, that host more biological productivity per unit area than almost any other ecosystem on Earth. The fluctuating salinity, the abundance of nutrients washed from the land, and the complex structure of underwater vegetation create conditions where organic matter is produced faster than it can be consumed. Salt marshes, the tidal grass meadows that fringe sheltered estuaries in temperate regions, absorb carbon at rates comparable to tropical forests, while simultaneously filtering pollutants from water flowing to the sea. They serve as spawning grounds for the majority of commercially important fish species along temperate coastlines. Juvenile fish spend the first months of their lives sheltered among the marsh grasses, feeding on the extraordinary abundance that the estuary provides before moving to the open ocean. Shorebirds feed on invertebrates exposed by the tide, while diamond-backed terrapins and horseshoe crabs complete ancient reproductive rituals on estuary beaches. These transition zones between land and sea are among the most important habitats on the planet, and they are disappearing rapidly as coastlines are developed and sea levels rise. Some of the most important medical and scientific discoveries of the past century came from the sea. The horseshoe crab, whose blue blood contains a compound called Limulus amebocyte lysate, is used to test every injectable drug and medical device for bacterial contamination before it enters the human body. Without this test, manufactured from horseshoe crab blood, modern medicine would be unable to guarantee the safety of vaccines, intravenous fluids, or or surgical equipment, deep-sea sponges have yielded compounds that led to the development of antiviral and anti-cancer drugs. Sea slugs produce chemicals that inspire new painkillers. Coral reef organisms have contributed to treatments for arthritis and cardiovascular disease. Ziconotide, a powerful painkiller derived from the venom of a cone snail, is used for patients whose pain cannot be controlled by other means. The ocean is a library of biological chemistry, refined by hundreds of millions of years of evolutionary pressure. We have barely begun to read it, and already it has transformed medicine, materials science, and our understanding of how life can solve problems. Scientists can trace the journey of an ocean current, not only by measuring its temperature and salinity, but by reading its chemistry like a fingerprint. Water that formed in the North Atlantic contains different ratios of oxygen isotopes than water that formed near Antarctica. The amount of dissolved nutrients reveals how long it has been since the water was last at the surface, where biological activity strips them away. Radiocarbon dating can reveal when the water last exchanged carbon dioxide with the atmosphere. Trace metals like barium and cadmium record the biological productivity of regions the water passed through. Every parcel of water moving through the deep ocean carries this chemical record of where it formed, what it has done, and how long it has been traveling. When oceanographers sample water at different depths from a single location, they are reading the layered history of currents that formed in different oceans, decades or centuries apart, are stacked on top of each other in the dark. Even now, as the world grows quiet around you, the ocean is moving. Somewhere, a deep current carries cold water from the poles toward the equator in the darkness far below the surface. Somewhere, a bioluminescent jellyfish pulses softly through the midnight zone, its light the only brightness for kilometers in any direction. Somewhere, a blue whale moves through the deep water, its call traveling thousands of kilometers before fading into the hiss of the sea. On a reef, fish rest in crevices while the tidal rhythm marks the hours. On the abyssal plain, marine snow drifts downward in slow spirals, carrying the faint memory of sunlight to a floor that has never seen the sky. The ocean has been doing this since before there was life to witness it, and it will continue long after the problems of this moment have passed into the sediment layer they will eventually become. There is comfort in that patience, in the deep, slow rhythm of a world that has survived everything and continues moving forward, inch by inch, degree by degree, wave by wave. Let that rhythm slow your breathing now. Imagine the press of dark water, the quiet of the deep, the weightlessness of drifting far below, where any storm can reach. The ocean carries no urgency, only motion and memory and the slow chemistry of time. Every molecule of water in your body has been in the ocean before. You are made of ancient sea. You have always carried its salt. And in the stillness before sleep, you can almost feel it, the quiet pull of the tide inside you, drawing you gently down toward rest. Let your thoughts drift like marine snow. Let the deep hold you. The ocean has remembered every creature that ever lived within it. It will remember you too, in its own way, in its own time. For now, there is nothing left to do but float in the silence, between waking and sleep, carried by something older than imagination. Good night.